In this video, I am going to explain you how to solve an memory RAM and ROM interfacing problem or example. And here this question is asked in the December 15 question paper. So here what is given? Our 8086 processor will be working in minimum mode configuration and there is a ROM size and RAM size will be given in that example. So now let's check with what is the size of our ROM and RAM. The size of ROM is the 32 KB of EPROM you are using 16 KB of devices and the third one is 64 KB of SRAM using 32 KB of devices. Now the first one, what is the first statement is given in that example? Your microprocessor 8086 is working in minimum mode and whenever it is working in minimum mode, that time your processor pin we are using that is MN and MX bar and that pin is connected to VCC. So this pin is connected to now VCC and now the second point is our 32 KB of EPROM using a 16 KB of devices. So I'm writing here 32 KB of EPROM using 16 KB devices. So first of all, we have to write here what is the total size of our ROM. So the total size of our ROM is equal to 32 KB and the available size of our ROM that is EPROM is equal to 16 KB. So in that example, we got two number that is first of all, we got the number that is 32 KB of EPROM. So 32 is the total size of our ROM and 16 is the available size of our ROM. So whenever I am writing here total and available size, I have to calculate how many sets will be required and how many chips will be required. So first of all, I am finding out number of chips will be required. So how we can find the number of chips will be required? First of all, what is the total size of our EPROM divided by available size of our EPROM. So in that available size of our EPROM, there is the data that is 16 KB of devices will be available out of 32 KB of our EPROM. So I'm writing here 32 divided by 16. So we got the number 2. So there are two chips will be required and now I have to calculate number of sets will be required. So number of sets we can calculate it as number of chips divided by number of banks. So as we already know there are two types of memory banking, even memory bank and the odd memory bank. So there are two types of banks. First of all even and second one is odd. So there are two types of banks are there. So I'm writing here number of chips we got that is 2 and divided by number of banks that is 2. So 2 divided by 2 that is 1. So we can say that there is only one set of EPROM will be available. So even and odd set one of our EPROM that we are using while drawing the diagram. Now let's begin with we have to calculate the address lines required for our EPROM. So how we can calculate the address lines required for our EPROM? What is the available size for our EPROM? That is 16 KB. And for 1 KB memory location, we are using 1024 memory location for each and every KB. So your 16 KB is nothing but you can write here 2 raised to 4 and 1024 is nothing but you can write here 2 raised to 10. So 2 raised to 4 into 2 raised to 10 I can write here 2 raised to 14. Suppose I got the number 2 raised to 14. So here 14 address lines will be required for our EPROM. So I'm writing here the statement that is 14 address lines required for our EPROM. Now we have to write down the line number that is address line number. So I'm taking here number A1 to A14. So why here A1 to A14? In case of our address bus, there are total 20 bit of address bus will be available. So how this 20 bit will be considered? First of all, I am writing here the size of our address bus is 20 bit. So out of that 20 bit, we are using that number A0 to A19. So this A0 signal will be assigned to our even memory bank location. And there is also burst high enable signal will be available that will be assigned to our odd memory bank. So A0 signal will be accessed by our even memory bank and the burst high enable signal will be accessed by our odd memory bank. So that I have skipped this A0 signal, that is our address line, and I am starting here from A1 to A14. Now we have to calculate the IC number for our EPROM. So I am writing here the IC number for EPROM is equal to what is the available size of our EPROM, that is 16 KB. So 16 KB into 8 bit, we are using here 8 bit because we have 8 bit of our devices, that is input output devices. So I'm writing here 16 KB into 8 bit, that is 128 bit. And whenever we are calculating the IC number for our EPROM, that time we are using the prefix that is 27 for our EPROM. So I'm writing here the number for our EPROM is equal to 27 and then 128. So 128 is the number that is we got from our calculation 16 KB into 8 bit, and 27 is the prefix that we are using for our EPROM. So it is the starting prefix. So each and every IC will consist of this number and then your memory location. Now we have done with our second part and our first part. So whenever the question will be asked for the 10 marks, that time you have to write down the description for all these statements. So this first statement is not having any marks. You have to just write down the statement. Your MN and MX bar pin is connected to VCC. In the second line, you have to calculate number of chips will be required, number of sets will be required, address lines will be required, and IC number for our EPROM. And based on that given data, you will get 2 marks from this. So for the second point, you will get 2 marks. The third point, you will get 2 marks. And whenever you are drawing the diagram, so diagram will get 6 marks. Okay, now I will forward to the third point. So in that third point, what we have to calculate? We have to calculate the same procedure for our RAM structure. So in that given example, the 64 KB of SRAM using 32 KB of devices. So I am writing here 64 KB of SRAM using 32 KB of devices. So first of all, I have to write here the total size of our SRAM. So the total size of our SRAM is 64 KB and the available size of our SRAM is equal to 32 KB. So the first of all, I have to find out the number of chips will be required. And these chips will be required, it will be decided on how many total number of chips will be available divided by available size of our EPROM as well as available size of our EPRAM. That is the formula we are using for number of chips required. So here the 64 KB of SRAM will be there, and out of that we are using 32 KB of data. So 64 divided by 32 is nothing but value 2. Now we have to calculate number of sets will be required. So how we can find the number of sets, that is number of chips that we got from our previous calculation, and number of banks. So there are two types of banks. So 2 divided by 2, we get the answer 1. So here we have calculated based on this data, that is 1 set will be required for our even and odd set of our SRAM. So I am writing here even and odd set 1 of our SRAM. So now what you have to do, you have to calculate the number of address lines that is required. So how we are calculating the number of address lines? So first of all, write down here address lines required for our SRAM. So here, how many address lines will be required? How we can finding out with the help of this formula? So we have the 32 KB of our available size. So I'm writing here 32 KB into 1024 memory locations. So 32 KB is nothing but 2 raised to 5 and 1024 is nothing but 2 raised to 10. So 2 raised to 5 into 2 raised to 10, we got the number that is 2 raised to 15. So here 15 address lines will be required. So here you can consider that whenever you are calculating the address lines, that time you have to check the what is the available size out of that SRAM as well as our EPROM. Now what you have to write the line number for our address line. So I'm writing here 15 address lines require, and here you can write the address line number for our SRAM. So 15 address lines are required for the SRAM and the line number for the address line is equal to A1 to A15. So these address lines will be considered whenever we are drawing the diagram with the help of minimum mode configuration. Now we have to calculate the IC number for our SRAM. So IC number for SRAM is equal to whatever the size will be available, that will be multiplied with our 8-bit number. So 32 KB into 8-bit, it will become 256. And the IC number for our EPROM, that is, we got already 27128, and here we have used 27 is the prefix for our EPROM, and whenever we are calculating the IC number for our SRAM, that time we have to use the prefix that is 62. So whatever number we got, that we are writing here after 62, so that my IC number for our SRAM will be 6256. Now we have done with our theoretical part of our question. So this part will be asked for the 2 marks. The second one will be for 2 marks. So here I have calculated the theoretical part for my example. Now we have to draw the diagram with the help of this our minimum mode configuration. So here you can check in this diagram, that is 8086 CPU is there and 8284 clock generator will be available, 8282 latch is there, and our 8282 latch consists of two signal, that is bus high enable signal and our address line. So I am extending this signal, that is bus high enable signal will be extended here, and now second one, the address line is also extended because it is required to connect to our memory RAM and ROM interfacing. Now again, I am extending this data lines as well as our memory read and memory write signal. Now check here in this diagram, in our example, we got in our second point, there is only one set of even and odd set of our EPROM will be available. So how we have find out this one set of EPROM based on that formula, that is number of chips divided by number of banks. So we require only one set of even and odd of our EPROM. So one set for even and one set for odd. So that I have drawn in that diagram, that is EPROM odd and 27128, then EPROM even 27128. Now we will go with our RAM structure. So in our RAM structure, it is also required 2 divided by 2, that is one set will be required. So there is even and odd set of 1 of our SRAM will be available. So first one is even set for our SRAM and the odd set for our SRAM. So here I have drawn this SRAM odd set 1 and our SRAM even set 1. and I have given this IC number that is 62256 because this IC number we got it from this calculation. Now, what is the next one? Whenever we have to draw this interface, that time we have to check these two signals. First of all, this RD bar and the second one is WR bar. So this read signal is connected to only our EPROM. So here that is a memory read signal will be available. So what is this memory read signal? That is MEMR bar. So this is connected with our 74138 decoder. And this memory read signal will be interfaced with our RD bar of our EPROM. That time we are doing a memory interfacing with our 8086 CPU configuration. Same it is followed for our memory write signal. So these are the two control buses are available, that is memory read and the memory write. So now I am connecting this line that is read and write bar in this diagram. So check here, this RD bar signal will be passed to our EPROM and that is for even and odd, same it is applicable. Now we have to consider here one point whenever we are connecting this data line to our EPROM as well as our SRAM, that time we have to check even and odd set of our memory bank. So whenever I am connecting this data to the even memory bank, that time I am considering here the D0 to D7 signal, that is our data bus. And for the odd memory bank, we are connecting D8 to D15 line. So that's why I have written here D8 to D15 in our odd set of memory bank and D0 to D7 in our even set of memory bank. So here is also for SRAM the same structure we are following. For the odd set we are writing here D8 to D15 and for the even set I am writing here D0 to D7. So now I have to connect this line for the data line, but before that I will go to the SRAM structure for our read and write. So now I have to connect this read and write signal. So always you have to remember only read signal will be available in case of our EPROM. But in case of our RAM, there are two signals, that is RD bar as well as WR bar. So here there are two signals are there, that is memory read and memory write, that are interfaced with our RD bar and WR bar of our SRAM structure. So I am connecting this line, that is RD bar here and then WR bar here. Same it is followed for our RD bar and then this is for WR bar. Now I have done with our read and write control signal. Now I have to draw these data lines with our memory interfacing diagram. So this is our data bus, that is from D0 to D15. Now I have to draw the signal for our bidirectional data lines to our data bus. So I am drawing this data bus here to each and every set of our odd and even set of our RAM as well as our ROM. But this line is bidirectional. So I am drawing this symbol for bidirectional data lines. And we have to specify the name of the data line. So I have specified here D8 to D15 for the odd set, D0 to D7 for the even set. Here is also I am following the same structure, that is D8 to D15 for the odd set and D0 to D7 for the even set. Now we have done with our data line. Now we have to begin with our address line. So in case of address line, first of all, take another different color of your line and this is our address line. So you can connect this address line and you can draw this line with the help of this memory interfacing diagram to our data lines and address lines of our 8282 latch. Whenever you are using the address line, it is configured in our 8282 latch. Whenever you are using the data line, so it should be provided by our 8286 trans receiver, that is our 8-bit of data trans receiver. Now I am connecting this address line here and this is a unidirectional line. So this symbol will be followed for the unidirectional line. So now each and every odd and even set of RAM as well as our RAM, we are connecting this address line. And here we have to specify the number that we got from our calculation. So here you can check for the EPROM, we got this address line, that is our A0 to A1 to A14. We have not considered here A0 because this is connected to our even memory bank. We are taking this number that is A1 to A14. So I have write here number A1 to A15 for our EPROM. And for the SRAM, we got this address line that is from A1 to A15. So I have written here number A1 to A15. Now we have to connect our bus high enable signal and our address line, that is A0, to our even and odd set of memory bank. So whenever this is an odd set of memory bank, I am writing here bus high enable signal for our EPROM as well as our SRAM. Now the next line is your even set. For the even set of our memory, we are connecting here the A0 line. And this will be provided to our chip select signal with the help of this OR gate. Now one input connection is completed, that is our bus high enable signal as well as our address 0 line. One input connection is still pending and that we have to connect with the help of this truth table. So whenever you are following this truth table, so Y0 to Y7, these outputs will be considered in our decoder. And here the even and odd set of SRAM will be available, that is 0, 0, 0 signal will be provided with our even and odd set of our SRAM. So whenever you are considering the SRAM, that time there are two types of bank, that is even as well as odd. And the same structure you are following it for EPROM. So for the EPROM, it also consists of even and odd set of our ROM. Now I have to select the whatever lines you require in that particular connection. So I'm writing here for the SRAM, for the even connection, the Y0 will be available, and for the even set of our SRAM, the Y1 is also available. So I'm writing here Y0 and Y1, these two signals are available. For the odd set of our SRAM, we are also using this Y0 signal, as well as we can use this odd set of SRAM, that is our Y2. So this Y0, Y1 and Y2, this will be used with our SRAM. Now this Y4, Y5 and Y6, this will be used with our even and odd set of our EPROM. So Y4 will be used with even as well as odd set of EPROM. So I am writing here Y4 in both the cases. And the next one, for the even set, I am only writing here the Y5, and for the odd set, I am writing here Y6. Now I have to select one of the line for connecting this one input signal. So first of all, our EPROM is an odd set. For EPROM odd set, I am using either Y4 or Y6. Suppose I am taking Y4 in one of the odd set of signal, then again I can't use this Y4 in our even set of our EPROM. So I'm writing here Y4 for the odd set. So this connection is already done. Then I'm taking for even, that is Y5. So I'm writing here Y5 in our even set of EPROM. Now the next part is, that is for SRAM. Suppose I'm selecting here Y1 for even and Y2 for odd. So I'm writing here Y1 for even and Y2 for odd. Now we have done with our connection, with our read connection, then write connection, data lines, address lines, then bus high enable signal, and based on that even and odd memory banking, we have connected to our input signal to our OR gate, and this will be going to the chip select signal. Whenever it is activated, this signal should be low. If it is a low, then it should be activated. If it is a high, then it should not be activated. Now check in this decoder, there are total 8 output signals are available, that is from Y0 to Y7. And here there are three inputs, that is A, B, C. So I'm writing here this line, that is A19, A18 and A15. We have total 20 bit of address bus, and out of that 20 bit, we are using this A0 signal for our even set of our RAM as well as ROM. And whenever we have calculated the address line, we got the number till A1 to A14 and A1 to A15. So this A1 to A15, we are considering this highest number for our address lines that are already utilized in our ROM as well as in our RAM. Now, which numbers will be remaining for our address line? If we are considering it for a 20 bit, then it should be A0 to A19. So A0 number is already done. A1 to A15 is already done. Now which address lines are pending? That is A16, A17, then A18 and A19. So these lines are remaining from our address bus. So these three signals that are considered here as the input, like A, B, C. You can select any one of the line for our A, B, C input. Now, which lines will be pending? We can also use that whenever we are using that input symbol, that time you can consider here this address line for our A, B, C will be our highest order data bus, and our higher order data bus will be A 17, A18 and A19. So this will be considered as the input. And here only one address line will be left, that is A16. So this will be connected to the D signal and that will be considered as a ground signal. So here in that diagram I have drawn the A16 as a ground signal and the 17, 18, 19 will be used as a input signal. So out of this four remaining line, you can use any three lines for our input. So here I am taking 17 to 19 as the input, and whatever the address line should be remaining, that I am connecting it to the ground signal. And this input will be connected as a D input signal. So here in case of decoder, we are taking only 3 H to 8 signals. So 3 are the input and 8 are the output. So this D signal will be considered as a ground signal. So it should not be reflected as the address line of our decoder. So in this way, we have drawn this memory interfacing diagram. So this question can be asked for a 10 marks and you have to write all appropriate discussion that we have done in this lecture. So you have to write down everything in your example so that you will get 10 out of 10 marks. So the description for our diagram and our diagram drawing, you will get 6 marks. And for this description, this is the theoretical part that we have calculated, number of chips, number of sets, address lines, then IC number. For this one, you will get 4 marks and 2 marks for each ROM and RAM. So in this way, you can solve this question in the exam.